Well, good afternoon. Welcome to session 2 of Math-120, year 2022. Let's start our time with prayer. Father God, thank you for this opportunity to study an expression of your wisdom and your beauty, which is the science of mathematics. Lord, may you bless our time together. Bless all these dear students, help them in comprehending different concepts in mathematics, and may it be that they be able to apply these principles into their lives and ministries. Lord, may it be through these studies we can gain a deeper understanding of your knowledge and the order, the pattern that you have set upon this world. We thank you, we praise your name, we pray all these things in the mighty name of the Lord Jesus Christ. Amen. Okay, as we start the week number 2, session 2, also wanted to remind you, please, if you have any prayer requests, please share those. There is a section on the bulletin board on your right-hand side that you can share your prayer requests. I'd be more than glad to pray for your needs, and we can pray for each other. Let's look at the syllabus first before we continue. Okay, we are here in week 2, and we are going to look at chapter 4. We will look at the system of numeration, and then you have assignment number 4, not assignment number 3, I'm sorry. We will look at Hindu-Arabic numeration system. The little known fact will be graded as assignments 4 and 5 for next week. But I encourage you to start working on it, but that's for next week. And again, I say that these assignments 4 and 5, the little known fact, it's open book. You can use the computer, Google. You can even talk to each other and share your information with one another. It's more like a research to help you to gain a deeper understanding of, especially in numerical system. Please submit your assignments on time. This week by Sunday, you're supposed to submit assignment 3, and I'll read Nichols chapter 3 also, and submit the reading report on that by Sunday. And there's a quiz that it's due Sunday before the midnight. Also, please, each of you pick one chapter from the book by Nichols. Let me know which chapters you have chosen and work on that chapter to prepare a PowerPoint presentation to do your presentation on the last session, week number 7. If it's not possible for you to do it live online, you can submit it to me, but I need to know as soon as possible which chapter you have chosen, because I don't want you guys to have overlap. I want you to choose different chapters, each student different chapter. Please let me know about that, okay? Let's go then to our PowerPoint. Okay, here. And excuse me. Today, we are going to talk about sets. That's foundation for mathematics. Let me go here. That's foundational for mathematics because math, we work with set all the time. The whole thing that we do, without set, we can't do mathematics. Basically, if you look at this picture, a set is a combination of different elements that are similar. For example, we have a set of dinosaurs, different dinosaurs, butterflies, vehicles, boats. Okay, so A set is a collection of objects which are called elements or members of that set. A set is well defined when its content, the elements, are clearly defined, are clearly determined. There are three methods are commonly used to indicate a set. You have description, you have a roster form, and you have set builder notation. I will talk about them, and I think that will make it more clear. So first, let's talk, let me move this from here. Let's talk about description of sets. For example, let's give you usually the best way to learn mathematics is by doing different example. You're asked to write a description of the set containing the elements Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. The solution you're describing. This is a descriptive way of presenting a set. The set is the day of the week. You're just describing it in plain English. Listing, no. If when you want to list the elements of a set, you do that, you use braces here, right? These here. And you put the element bit here. And when you do that, and you also use comma between the element, this is called a roster form. Roster form, and you separate the elements by comma. So if I want, this is a descriptive way of defining this set. If I want to use roster form, I put Monday, Tuesday, the name of the 7 days of the week, and I put comma between them. This is a roster form. But for example, the elements are 1, 2, and 3. But this is not a roster form. This is not a roster form because I'm using either parentheses or brackets, and they do not indicate a set. Now, you can also put a name with a capital letter. The set are generally named with a capital letter. For example, if we have a set of natural numbers, we will get to that. You use, or the counting number, you will use the capital letter N. Here, 1, 2, 3, 4, 5, and continues. And the 3 dots or 3 ellipses means that indicate that the elements in this set continue in the same manner. 6, 7, 8, 9, 10, and so on. Okay, so this is a name. You have the braces, you have the elements, and they are separated by a comma. Now let's look at the roster form of a set. Express the following in a roster form. A set A is the set of natural number less than 5. You got to pay attention to the problem if you want to give the correct answer. So here, I call it A. You put the braces. Natural numbers are 1, 2, 3, 4, 5, 6, 7, 8, but you want less than 5. So the elements are 1, 2, 3, and 4. Question number 2, set B is a set of the natural number less than or equal to 75. Pay attention when we say less than or equal, it means it includes 75. So you can write 1, 2, 3, 4, and then you put those 3 dots or ellipses. It means it continues the same manner all the way up to 75, including the number 75. Or the set P is a set of the planets in Earth's solar system. So call it P. You have the braces, and then you have the names of the planet. Mercury, starting from after Sun, after Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. When we use the word inclusive in a set, it's very important. For example, the set of natural numbers between 4 and 9 doesn't include 4 and 9, 5, 6, 7, and 8. But if I say the set of natural numbers between 4 and 9 inclusive, I mean between 4 and 9 including 4 and 9. So it goes 4, 5, 6, 7, 8, 9. So you see that here it's only, I say between, here I say between 4 and 9 inclusive, meaning you must include these two numbers. Okay. Then we have a set builder notation or a set generator notation may be used to symbolize a set and is frequently used in algebra. That's I said in the beginning. Without set and set theory, we can do no mathematics, no algebra. When you have this symbol, which looks like an E, you can read that is an element of whatever set. This symbol indicates that the element, whatever, is a part of a different set. For example, if I have a set A, which is natural number 5, 6, 7, and 8, we can say 6 is an element of set A. But we can also write 9 is not an element of set A because 9 is not in these numbers. Okay. So the set builder notation, remember in the test, in the quiz, don't forget that when we talk about the set builder notation, we have these braces. All x, now x can be number, whatever, such that x is less than equal to 2. Do you know this is like any language. Math is a language. It has its own vocabulary and grammar. So when we see something like this, you got to know that. You got to memorize it. This means it's a set of all x such that x is less than or equal to 2. So it includes 2. Right here, for example, when we say we have this number, x, here I'm defining the range of x less than a. So if I want to use set builder notation, I put these braces. I say all x such that x belongs to natural number and x is less than 4. So that will be only 1, 2, and 3. These are natural number and it's less than 4. Doesn't include 4. But if I change just one thing here, I put this, you see this bar makes it look like an equal sign. Then I'm saying all x, which are less than a, in this case, a is 4, in such a way that the numbers are natural numbers, is less than and equal to 4. So now you add number 4 here. Before you didn't. Let's say here, an example here. X is greater than a, and a is defined as all x such that x is part of a natural number and a is 4, greater than 4. So all numbers natural number greater than 4 start 5, 6, 7, and 8. And I put 3 ellipses or 3 dots here because this continues to infinity. Now, if I say greater than equal to a, so all x such that x is a natural number and x is greater than and equal to 4. You need to have a 4. I mean, you need the value of a must be given to you. So a is given to us as 4. Now, in this case, is greater and equal. So you see the difference. In the previous one, we started from 5. Here we start from 4, 4, 5, 6, 7, because we have greater than or equal to 4. Now, you may have a set like this. X is greater than A, but is less than B. So X, all natural number, which is greater than 4, but less than 8. So all natural number that are greater than 4, 5, 6, 7, it continues. But the second limitation, second boundary tells me that it cannot go more than 8, or it can't even have 8. So it's 5, 6, and 7. But notice the next example. If I just add, I put that bar here, it becomes all x, part of a natural number, greater than equal to 4, less than equal to 8. Now you add 4 and 8 here because you have these equal sign. Or you can have 1 on one side, but not the other side. For example, x, part of a natural number, greater than equal to 4, but less than 8. So you go 4, 5, 6, 7, but you do not include 8 because it's less than 8. Or you can have it, put the equal sign on the other side. X, all natural number, greater than 4, less than and equal to 8. So it goes 5, 6, 7, and 8. I hope this is clear. So what's a cardinal number? The cardinal number of a set is the number of elements in that set, distinct element in that set. And the way we write it, we say n of a. The cardinal number answers the question, how many elements are in a set. For example, let's look at page 50 of our textbook. Okay, page 50 of our textbooks talks about find the cardinal number for a set. Number A is set 7, 9, 11, and 3. How many distinct elements are there? 4. So the cardinal number is 4. Or let me write this. Probably this is easier. Would be easier for you guys to see. So let me come out of the share screen here. And need to go one moment. Just give me a moment so that I get this thing going. Okay. 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 All right, let's go to share screen. All right. First, let me clean this here. Okay. Okay. Then, example 8, page 50. For example, we have a number B. We have a set B equal to, then we have the set which is, its member is only 0. Now, what's the cardinal number for here? Don't say 0, don't say nothing. There is one element here. 0 is a number. So the answer for that, the cardinal number n of B is 1. Okay. Or let's look at, it said set D, and it says the example D, and you have this symbol. This symbol means null, nothing. So what's the cardinal number for that? This is an empty set. Again, let me write it better. It's kind of hard to do that. Okay, this means an empty set. And the cardinal number is 0. So pay attention to the difference between here and the difference here. Set B, the cardinal number is not 0 because it has one element, 0. But the cardinal number is 1. But this is an empty set, the cardinal number is 0. Or you have, as an example number C. Okay, and then you have a set of, you have, these are the elements, 13, 14, 15, and then I put 3 ellipses all the way, it goes to 22, 23. 22 and 23. So what's the cardinal number? What's the n of C? That's what we're trying to find. What's the n of this set? So remember, when we saw these 3 dots, it means it continues the same way. So you have 13, 14, 15, 16, 17, 18, 19, 20, 21, and then 22 and 23. So you have 11 members. So the n of that set is 11. All right? If you have questions, don't hesitate to ask me. All right, let me here. Okay, then let's go back to our PowerPoint. Okay. Um, we can have finite or infinite set. A finite set is a set A is a finite set if n of it, the cardinal number, the number of members of this set, its element, is equals to 0. That is, A is an empty set, or n of A is any natural number. So either we have an empty set or any natural number. Then we have a finite set. When a cardinal number is 5, cardinal number is 11, that's a finite set. A set whose cardinality is not 0, or it is not a natural number, is called an infinite set. For example, this set of all natural number, it goes 1, 2, 3, 4, 5, 6, continues. That's an infinite set because it has infinite members or infinite elements. Now, the universal set is all the elements or members of any group under consideration. Now, you can have, so understand the difference between finite, infinite, and universal set. Its cardinal number is infinite and is assigned by the symbol Aleph Null. That's from the Hebrew alphabet. Aleph Null. Okay, that's the cardinal number for an universal set. Okay. Now, equality of set. A set A is equal to set B when it means that the set A and set B contain exactly the same elements, regarding of their order or possible repetition of the elements. We symbolize equality by A equal to B. For example, if set A is a set of these 4 letters, W, X, Y, Z, and B is Z, Y, X, W, X, the two are equal, even though the orders are different. So we write A equal to B because all the elements in this one is also here. Let's look at page 53. There is also a different example on page 53. Example 10. We can go to our tablet if you want. I'm trying to make this a little bit thicker. Okay, this would be better. For example, we have on page 53, page 53, example 10, number A. We have one set which is 4, 8, and 9. And then we have another set which is 8, 9, and 4. These two are equal because all the members here are here too, no matter their order. Let's look at okay, let's look at example B. B, I mean, under example 10b, we have one set which is 1, 3, and 5. And then we have another set which is 0, 1, 3, and 5. Okay? They are not equal because this one has 0 and this one doesn't. So don't assume that just because it's 0, it's nothing. 0 is a valid number, very important number in numerical system. So these two are not equal. All right. But let me, it's an interesting example follows. It has a question. If you have 4 and 5, and then you have another set, 4, I mean, actually, where is it? Okay. And actually you have 5, 4, and then you have this null or void. I'm sorry. You have, okay, sorry. My drawing is not that good. 4 and 5. Okay, these two are equal. Why? Because this is nothing. This is null. This is empty. This is the null symbol, which is like this. Okay, that's different than 0. So these two are equal. Be careful of these tricky questions. Okay. Let's go back to our PowerPoint. Now, subset. Set A is a subset of set B, and then we symbolize it by this. We say, this like belonging to B. And then if we put here, it means it's also equal. If and only all the elements of set A are also in elements of set B. Set A is not a subset of set B, then you use this symbol, you cross it. Now let's look at example on page 57. Now you have on page 57, example number 1, A. You have a set A which is 1, 3, 5, 7, set B which is 1, 3, 5, 7, 9, and 11. Are they equal? No, because set B has number elements 9 and elements 11, which is not in set A. Let's look at the second one. It's an interesting one. So let me go to the tablet. Okay, and let me again try to. We have okay, this is on page 57, example 10, example 1. Okay, now number B, that's an interesting one. It says set A is a set, and we put the braces, all X such that X is a letter in the word proof. X is a letter in the word proof. Okay. Proof. Okay. And set B such that X, all X such that X is a letter in the word roof. I mean, not X, Y. Sorry. Y in such Y, all Y such that Y is a letter in the word roof. Now they say the question is this: what's the relationship between A and B? Is A a subset of B? No, it's not, because here we have the letter P, which is not here. So it's not a subset nor equal. So we cross it. So that's something you got to be careful. All right. Let's move on. Okay. Proper subset. If set A is a subset of, but not equal to B, then you say not equal to B, then you say it's a proper subset, meaning the elements in in the set A, you're all part of in set B, but set B has one or more elements that are not in set A. For example, in that example of the word proof and roof, set B is a proper subset of set A. All the letters in the word roof you can find in proof, but they are not, it's not equal, because roof doesn't have P. Okay? So if you look at page 58, for example, it has one set is 1 and 3, the other set is 1, 3, 5. Set A is a subset of set B. That's true, but it is not equal. So we use either this symbol, or we say this is a proper subset, or we use this symbol when they are exactly the same, they are equal. Okay, for example, on page 59, if you look at your page 59, you have a set 2, 4, 6, 8, and set B is 2, 8, 4, 6. They are, you use this symbol, because it's A is a subset and equal, so it's not a proper subset. to be a proper subset, they should not be equal to each other. Okay. Or if you have, it says set A, all X, X is a person and X lives in San Francisco. Set B, X, all X, X is a person and X lives in California. So what's the relationship between A and B? A is a subset of B, but they are not equal because it says, yes, all people who live in San Francisco also live in California, but set B has a lot more people who live in different cities in California. So they are not equal. So set A is a proper subset of set B on page 59, example A. Okay. The other symbol is, so this is a symbol for proper subset. This is a symbol only for subset when they are equal. All right. Oops. The empty set is a subset of every set, and it symbolizes by the symbol null, nothing. Nothing is a member of everything. Furthermore, the empty set is a proper subset of every set except itself. So for any set B, the null is a it's a subset of set B. This is number one that we said. B, for any set B other than the empty set, the null is also subset of any set when it's not itself. When it's include itself, it cannot be, because then they become equal. All right. So please remember to know the difference between set presentation, roster form as a set builder, and the difference between less than, equal, inclusive, proper subset, or is it a proper subset or is it just a subset? Proper subset means the set A, all the elements in set B are in set B, and they are equal. They are the same, exactly same elements for subset. The proper, I'm sorry if I, let me repeat myself. For the proper subset, A is a proper subset of B when all the elements of set A are in set B, but they are not equal. If they are equal, you just say they are subset. Okay. And null, nothing, the empty set is a subset of every set. And empty set, it becomes also a proper subset of every set except itself. So if set A is null and set B is null, they are not proper subset. The set A is a subset of set B, but not a proper subset, because they are equal. They just have one element, and that's null. Okay, now we come to diagramming and using this kind of diagramming to visualizing mathematical structure. That's very helpful in lots of statistical study. Complement. For example, you say here A and A prime, they are complement. Together, they form a universal set. Complement of set A, which is symbolized by A prime, is a set of all the elements in universal set that are not in set A. So complement of set A is A prime, because these two together form the universal set. So the complement of set A are all the members that are not in set A, but they are in the universal set. And together, A and A prime form the universal set. We have intersections and union. You know, here in this picture, you have A and B, these two circles, red and green. Their intersection of A and B is this yellow part, and it's indicated by this. The set C, the blue set, the intersection between A and C is this purple one. The intersection between all three is this white one right here. A intersection B and intersection C. So it means an element here is common in all these three sets. Element here is common between A and B. Okay. The union, no, we have intersection and union. A union of a set A and set B is symbolized by U here, like this symbol, and it includes all the elements that are both in set A and set B. So we have here we have set A, here we have set B. The union, it includes all the elements. And when we do that, we are doing union operation. Here it's called Venn diagram. You have, for example, set A, set B, and set C. Set A, all the members here, A, D, G, and E. Set B, all D, G, F, and B. Set C is C, E, G, and F, and there's nothing outside. For example, let's say we have two teams, two sets, one plays soccer, one plays tennis. Alex, Casey, Drew, and Hunter are in soccer team. Casey, Drew, and Jade also in tennis. So right here, you can see there are some who are in both teams. So the union of the two would be everybody, both elements from both sets. Whoever plays soccer and whoever plays tennis together. So the union of these two will include everybody: Alex, Casey, Drew, Hunter, and Jade. But the intersection are only two people. Only Casey and Drew play both soccer and tennis. Okay. Now, you may have the difference of the two sets. So we are looking at people who only play soccer. They don't play tennis. So we take the soccer, all the members of soccer, and subtract all the members who play tennis. So we end up with only Alex and Hunter. These two guys are the only one who only plays soccer, not soccer and tennis. So we have U for union, either. This symbol for intersection, that must be both set. And the difference is in one set, but not the other. Okay, again, these are like vocabulary of mathematical language. Please learn them, memorize them. So let's look at three sets. We add another one who plays volleyball. So we have 4 sets now. We have a team for volleyball, soccer. A team for soccer, tennis, and volleyball. Okay. And these are the members of the volleyball team: Drew, Glenn, and Jade. So if you want to show it as a Venn diagram, we write these 3 and we put them here. This diagram tells me, for example, Drew here plays soccer, tennis, and volleyball, because Drew is in the intersection of all 3. Jade plays tennis and volleyball. Casey plays soccer and tennis. Okay, and no one plays only tennis here, but you see here the difference. We don't have anybody that plays only tennis. They all play tennis plus something else. So if we want to talk about set S, is Alex, Hunter, and Casey and Drew. Alex and Hunter play soccer. Casey plays soccer and tennis. Drew plays soccer and volleyball. Union of set T and V, meaning people who play both tennis and volleyball. It includes Casey, Drew, Jade, and Glenn. We have 4 members. We have T union V, and these are the elements. Intersection of S and V, meaning only people who play both soccer and volleyball, and that's only one person. That's Drew. Okay. And well, what is this? An empty set. The intersection of set S minus set V, meaning people, the only, this is an empty set right here. We want people who play volleyball, but not soccer. We want people who, we have intersection of S and V. So the S and V, intersection of set S and V is Drew and Jade. But we don't want them to play tennis. So it cannot be part here, so it would be only here. No, nobody, that's an empty set. So we are talking about people who, we want to know people who play soccer and tennis, but not volleyball. Nobody. I hope you're following. Okay. Universal set would be, you see, if we have here S, T, and V, these are the members. Now, if it wants to be universal, you have to include members who do not play any of these things: Blair, Erin, Francis, and Ira. So you have to include them, and that will become the universal set for whatever particular group or whatever segment of society that we are looking at. If we want to know everyone who doesn't play soccer, so here's the S, and here the intersection between S and T and S and volleyball, which is Drew. So everyone who doesn't play soccer would be Jade. Who doesn't play soccer would be Jade, Glenn, Blair, Erin, Francis, and Ira. And you have them all here. Okay. Everything that is not S. So you want S prime. You're looking at the complement of S. You want people who play something or don't play anything, but they don't play soccer. So that would be here, Jade and Glenn and these 4 guys here. Okay, let's look at example 68. In example 68, example 3, page 68, it has the set U. It goes all the numbers, natural numbers from 1 to 9. And set A, it is 1, 3, 4, 7. Ask you to find A prime. Let's do that on the tablet, because you have these kind of questions, your test. Okay. So we have all right. So we have first set is U, which is all the natural number from 1 to 9. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Then we have set A, which is 1, 3, 4, 7. 1, 3, 4, 7. Please remember to use braces, not brackets or parentheses. If you use that, that doesn't indicate a set. And we want to find A prime. So this is like a universal set. This is A and A prime. A prime is something that when the union of A and A and A prime should give you all these numbers. So the universal set is a union between A and A prime. So what should be A prime? So that together with A gives us all number. So we look at these number 1, 3, 4, 7. We cross them here 1, 3, 4, and 7. So this set must include, if it wants to be the complement of A prime, must include 2, 5, 6, 8, and 9. Okay? So this is the A prime, because together they give you the universal set. All right. Okay. Why are sets important? As I mentioned, this is the language of mathematics. They help us to treat a collection of mathematical objects as a mathematical object as itself. It's a starting point of mathematics, and a starting point of mathematics is like any language. You have vocabulary, definition, and rules. That's what you need to learn to do good in mathematics. And once you understand the principle, I think math is a very easy science. Once you understand the basic meaning of the principles. One of the things that we'll discuss later, a function. A function is a rule that basically takes a number or numbers to other numbers. What does a rule mean? It can seem quite vague at times. For example, 2x, it's the same rule as 2x plus 1 minus 1. Why? Because these two cancel each other. You take any number here and you put it here in this function, and take any number and put it here, any natural number, you get the same result. There are different rules in that they are calculated in different ways, but they always yield the same output. Hence, we can define a function as a set of ordered pairs. Now, when we get to chapter 6, we'll discuss domains of function. A domain is where the function starts getting its data. Function maps numbers to numbers, but the same concept of rule that maps things to things pops all over. You have, a function, and then you have operators. Operators map functions to numbers. And now we will discuss that. You will understand that once you see example. Operation in a groups maps abstract group elements to other elements. Other strange function might map equivalence classes of infinite sequence to finite set of rational number. You can't precisely pin down what things means unless you have a mathematical notion of an arbitrary set, and that's why we need a set. Right now, this may sound kind of abstract and confusing. Don't worry. As we go ahead, you will understand and you will see these things in examples. Basically, in algebra, any algebraic structure or topological spaces in geometry are both considered as a set with operations on it. The whole power of algebra, the things that we can do with math and modern algebra, is that it can apply to any set of things as long as the operations obey certain rules. That's why understanding sets is so important. So let's go to numerical system and kind of the history of the numerical systems and different numerical systems that we had in human history. the numerical system that we have used and we are using right now is Arabic numerical system, Hindu-Arabic. These are different, Hindu-Arabic, Romans, Greek, Egyptian, Mayan, Babylonian, Mayans. We will get to them. A system of numeration consists of sets of, you see again here, you see the importance of definition of set, basic numerals and rules for combining them to represent other numbers. Now, a thing very important is those useful functional numerical system are usually place value or positional value numeration system. It means the value of symbol depends on its position in that number. For example, consider number 20. The digit 2 in 20 represent 2 tens. It's in a second position. If you start from this way, from right to left, first, second, it's in a second position. It represents 2 tens. 200, first position, second position, third position. This represents 200s because this is one position, 10, 100. A true positional value system, you need to have a base and a set of symbols, including a symbol for zero. It's very important. And one for counting number less than the base. And the most common positional system, the one that we are using, is base 10, which is called decimal number system from the Greek word deca, 10. Okay. In Hindu-Arabic numeration system, that it's the one that we are using, requires fewer symbols, and that's why it's survived, and that's why we are using it. Because the other numerical system, they were just very cumbersome. They couldn't be helpful when you get to a larger algebraic or mathematical operation. But this requires fewer symbols to represent numbers as opposed to other numeration system. Basically, you have, that's all the number you need, 0 to 9. And these are called digits. For example, if you have number 12, it's 1 and 2. Numbers from 1, and also numbers from 1 to 12 have their unique names. 13 through 19, they have teens ending in a blended with names for numbers from 4 to 9. Numbers from 20 to 99, the 10 place is named first, followed by a number from 1 to 10. Numbers from 100 to 999 are a combination of hundreds and previous names. These are pretty obvious, friends. You get all these things. You have 30, 20, 15, 100, 570, 5,083, 56,000s. Okay. Now, we have also exponential notation. This is an exponential notation. B to power of n means b times b times b, where b appears as a factor of n times. Like and n is a natural number. When we write b of n, we say b the nth power of b. B or b to power of n, the nth power of b. And this expression is called exponential expression. B to power of any number, b to power of 1 is always equal to b. And remember this, any b to power of 0, any number to power of 0 is equal to 1. Okay. Let's look at example 1 on page 105. Okay, let's And for this, we can go to our tablets. Okay. No, sorry. Here we have on page 195, example 1. These are exponential numbers. For example, 10 to the power of 2. 10 to the power of 2. So the 10 is our B. This is our N. This is N. This is our B. 10 to the power of 2 means 10 times 10, which is equal to 100. Or, the same things, 10 to the power of 4 means 10 times 10 times 10 times 10, which is equal to 10,000. 1, 2, 3, 4, 0, and you need to have 4 zeros. Notice 7, if our base was 7 to the power of 1, is equal to 7. And if I had 7 to the power of 0, the answer is 1. All right? So that's for that. Now, as I mentioned, these numerical systems are positional. The Hindu-Arabic system it's a positional numeric system, meaning the positional value in the Hindu-Arabic system are this. Start from here, start from right to left. This is to power of, this is position 1. Basically, if the base is 10, so when you start from here, you have the first position, it's position 1 minus 1. Now I get to that. So it's to power of 0, which is equal to 1. Position 2 is 10. Position 3 is 100. Position 4,000. Position 5th is 10,000 and 100,000. So to evaluate a number in Hindu-Arabic system, we multiply the first digit on the right by 1. We multiply the second digit by 10, the third digit by 100, and the fourth digit by 1,000. If you notice that this is the fourth digit, so it's 4 minus 1, you get 3. So for example, if you have a number 572 and you are asked to expand that, it means you write, start from here, 2 multiplied by 1 because it's in position 1, 7 multiplied by 10, and 5 multiplied by 100, you get 570 plus 2, 572. So if you notice, what we do is basically from right, if you have a, it's 10 to the power of n minus 1. If it's the position, it's a first position is 1, n is the position of the number 1 minus 1, 0, any number to the power of 0 is 1. So therefore, when we multiply the digit 8 places from right, we get 10 to the power of 7. The place value rule, we can write a number in expanded form. If we are asked to write it in, for example, if I've given you this number, 1,234, and you're asked to write in an expanded form, it means write it this way. First, look at the number 1,234. You have 4 digits. For each of them, open a parenthesis. 1, 2, 3, 4. 1, 2, 3, and 4. This is the first position. 10 to the power of the first position, 1 minus 1 is 0. And any number to the power of 0 is 1. This is a second position. It becomes 2, second position, 2 minus 1, 1. So it's 10 to the power of 1 becomes 10. And this becomes 10 to the power of 2, 10 to the power of 3. And you multiply those and add them together, you get 1,234. So this is an expanded position, either this one or this one, okay? We have Babylonian numeration system, oldest numeration system, actually. It's a place value system with a base 60 instead of 10. Sexagesimal system, it's called. And it's not a true place value system because they didn't have 0, and it creates lots of confusion and difficulty in numeration. The positional value in the Babylonian systems are like this. So again, the first one, n minus 1, 0, so it's become 1. 60 to the power of 1, 60 to the power of 2, 60 to the power of 3. Let's look at pages 197 and 198. Okay. Okay, let's go to our tablet. Okay. Now, in this kind of problem, the value in the Hindu-Arabic numerical system, it must be given to you. For example, on page 197 of your textbook, page 197, you have table 4.1. You need that. That needs to be given to you, table 4.1. And it gives you, for example, the Babylonian numeral system with this symbol and this symbol. And it says this is equal to, in Hindu-Arabic system, to 1, and this is equal to 10. Now, then it comes and asks you, for example, if you have this kind of numerical system in Babylonian writing, and then this one, and then this one. If you want to write it in our numeric system, okay, you look at it. We is, each of them, if you want to write, remember, we is 1. So just put 1 here, multiply. Don't worry about anything else. Put a parenthesis, plus. Then the second number, second symbol, we, and is 10. So you have 10 times, now we get to the base later, just want to start with this, and the 2 of these we means 1, 1, 1 plus 1, okay? And put another parenthesis here, multiply by something, okay? Now, we want to know what to put here now. Okay, we said this is base 60. So we know it's base 60. But then this starts position 1. 1 minus 1 is 0, okay? This is position number 2. It's 2 minus 1, sorry. 2 minus 1, which is equal to 1. This is position 3. 1, 2, 3, or 1, 2, 3. So position 3 minus 1 is equal to 2. So for the word 60, not the whole parenthesis. So this is what you have. 1 times 60 to power of 2 plus 10 times 60. Remember, this is a base 60, 2 minus 1. Why 2 minus 1? Because this is the second position, and the rule is n minus 1 for whatever the base system is. This is the basic system is 60. So you get 2 minus 1, 1. And then plus, you have here 1 plus 1, 2 times 60 to power of 1 minus 1, which is 0. Okay? Now, 60 to power of 0 is 1. 2 times 1 is 2. All right? Plus 60 times 10. 60 to power of 1 is 60 times 10 is 600. Plus 1 times 60 to power of 2. 60 to power of 2 is 3600 times 1 itself. So you get, this is a number you get. You add them up together, you get 4202. So this number in Babylonian system, this number here, sorry, is 4202 in our system, this number. Okay, that's how you convert it to our Hindu Arabic system. All right, but you need to have that table. You need to have this information. Without it, you cannot do it. Okay, so okay, let's go back to our PowerPoint. Okay. Mayan numeration system, again, you need to have this table in order to answer the questions, the Mayan codes. Now here, remember, please notice I have simplified the numbers to make things easier from our textbook. But basically, that's the, if you look at it, if here is our Mayan system number, we want to convert it to our own Arabic Hindu numerical system. And remember, if you look at page 198, you need to have table 4.2 to answer that. When you look at table, and remember, these things go vertically. So this is position 1, position 2, position 3, position 4. So this number, this symbol here, if you look at table 402, is equal to is 10. Okay. But first, let's find these numbers. Don't worry about the position. So this is 10. This number, this owl shape, is 0. The dot is 1. 2 dots with 2 bars under them is 12. So write these things down. Then you want to multiply these by their positional value, which is kind of strange, because, and you need to know that the first, or kind of memorize it, the first position is always position, the 1 is 1, the second one is 20, the third one is actually, let's see, it's 20, it's 420 times 2, okay, here, 400. You can see that also very well on page 199. The first one is 1, the second one is 20, the third one is 18 times 20. I made it simple, I simplified that. Instead of 18 times 20, I wrote it as 20 times 20, 400, okay? And the fourth position is 18, it's a base 18, 18 times 20 to power of 2. I just made it to 8,000 instead of 7,200 to make things simple, to simplify the numbers. So again, You look at this here, you go to table 4.2, you find their value in Arabic numerical system. Then the position is kind of tricky. This is, first position is 1, second position is 20. The third position is 18 times 20. The fourth position is 18 times 20 to the power of 2, which I simplified them. You multiply and then you add them together. This is a number you get. All right. I think we did that actually. No, I did that right now. Example 5 and check and find pages 198, 199. If you want, we can do the one on page 199 with the tablet. Okay, but again, remember, you need to have table. This is page 199, and you need to have table 4.2. Otherwise, you can't do it. And these are the symbols, the Mayan numerical symbols that you have. From top to the bottom, you have this, then you have this oval-shaped symbol, then you have this symbol, and then you have this symbol, okay? You will look at table 2, we find that this is symbol for Arabic numerical system 14. This is 0, this is 7, and this is 12. These are given to us. You multiply it by a base, okay? The base here is a kind of Mayan, is kind of a tricky, confusing base system. This is the first one. So any number to power of the first position, 0 is equal to 1. So this is simpler, is 1. This is the second position is 20. Just remember that. The third position is 18 times 20. This is probably because of their calendar system, that they needed to fit this information in their calendar system. And then the third position is 18 times 20. Now, this is the fourth position, 4 minus 1, which becomes 3. Actually, oh no, as I tell you, this is doesn't go that way because of their calendar system. So it has to be power of 3, but actually they have it as a power of 2. So you just need to remember these things. In Mayan, in the quiz, remember this. Okay. That this is to power of 2. So remember, just remember these things. First position is 1, the second is 20, the base, the third is 18 times 20, and the fourth is 18 times 20 to the power of 2. Okay? And then you do the multiplication, and you add the numbers, and when you add all the number together, this becomes 1,500. This becomes 0, 0 times any number 0. This becomes 140, and this becomes 12. You add them together, and you get 100,952. No, so this number in Mayan is equal to this in Arabic numerical system. All right. Okay, so all right. let's go to our PowerPoint again. Now, here we have the Greek and then the Roman numeral system. This is the Greek numeration system, 1, 2, 3, 4, 5, all the numbers, 9, 10 to 90, 100 to 94 with the Greek alphabet and their pronunciation. Okay? And this is a Roman numeration system, very cumbersome. And that's why these numbers, this numeration system didn't last, because they're huge numbers. To write them, you want to write a number, you get to have all kind of alphabet, and it just doesn't work. And this civilization, actually based upon these numeration system, they collapse because of their numeration system. For example, let's look at some of them for you to see. Look at number 154. We want to find its Roman numerals. 154. Let's go. You see the 154 is, if you look at, we have the major ones. C is 100. L is 50. And IV is 4. IV is right here. IV is 4, if you can see that right here. So you have the numeration would be CLIV, or 1492. Okay, M is 1,000. When you have C is 100, when you have 4 of them, you get 400. Then LXX. LXX is 80. Okay. Then actually LXXX is 80. Then X is 10 plus 2, 1, 12. So in order to write 1,492, you got to write all these numbers. Or even worse than that, if you want to write, you see, just notice going from 1,400 to 3,000, just going up almost by 2,000. Notice how large this number in Roman numerals is getting. So you have 3M, which becomes 3,000. You have 4 C's become 400. You have L, again, 3 with 3X, that becomes 80, and XV is 15. So you get, that's how when you add them together, you get 3,495. Just think of it, you want to add these two numbers, it's just impossible. Multiply, division, that's impossible to do with this numerical system. We have Hebrew numeration system, which is basically, it really doesn't have a base, because they're not positional number, like the Roman numeral system. And that's why these numeration systems didn't last. For example, if you want to write 764 in Hebrew system, this is the number from right to left. Because if you look at it, going from right to left, this is the first letter, 400. Then you have the second letter here, 300. Then you have the 60 right here. And then you have the 4, which is right here. So that's the number you get. So you get 400 plus 300 plus 60 plus 4, 764, written as this. And again, it's not a real positional system. In positional system, any counting number greater than 1 may be used as a base for a positional value. If a positional value system has a base B, then its positional value will be like this, what we saw in Arabic and even in the Babylonian, in the system Mayan is kind of crazy. The Roman and Hebrew are not really positional value system, but basically like this. It's the position, the first position minus 1 becomes 0. Any number to the power of 0 is 1. So you see this 1 here. Then you have the second position number minus 1 is B. Now, if it's a positional value 8, would be 8. Positional value 2 will be 2. This is called, 2 is called binary. This is called octal. Then, so it's the position minus 1. So it's, you see 1, 2, 3, 4, 5. 5 minus 1, you get number 4. And these are the numbers. So the base 2 is binary, base 8 is octal, base 16 is hexadecimal. All right. Now, this is kind of tricky. Converting bases less than 10. For example, a number is given to you in a numerical system which is base 6. We want to convert that to 10. Again, don't be afraid. It's just remember this rule. 453, 6. So you write the digit 4, 5, and 3. First position, multiply by 1. The second position, the base, it's base 6 minus, wait a minute. So the second, it's a second position, which is base 6. Yeah, it's the second position, which is 2 minus 1 is 6. This is the third position, so 3 minus 1 is 2. So you multiply this thing and you get 177. So number 453 base 6 is 177 in our numerical system. All right. Now, let's say we are given a number in base 8. We want to convert it or expand it, write it in an expanded form and convert it to our numerical system. 3615 base 8. Again, write down the digits. 3615. It's base 8, so you have 8 for all of this. There is an 8 here, but it's to the power of 0 becomes 1. This is a second position, minus 1, 1. Third position, minus 2, 2. Fourth position, minus 1, 3. So you raise it to this power and multiply them, you get 1,933. Okay. Converting base 2 to base 10. Let's say a number is given to you in a binary system, base 2, and you want to convert it to our numerical system. This number, you got 101,101 base 2. So what do you do exactly again? Write all the digits 101,101. So it's base 2. So all of them get a 2, multiply by 2. And again, remember, there's a 2 here, but because it's base position number 1, 1 minus 1, it becomes 0. So it's 2 to the power of 0 is 1. 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, and 2 to the power of 5. So you see, this is 6th position minus 1, 5. So you raise them to that power, multiply and add, you get 45. Okay. Let's see. Let's go to page 204.